Hey kids, welcome back to this problem. The answer is choice 4. It doesn't speed up or slow it down, but it doesn't have no effect. A centripetal acceleration changes the direction of velocity. So that's a really important idea. We'll talk about that more in a little bit. I'm glad you're all safe at home right now and keeping your brains active. You should also try to keep your bodies active too. Now's a great time to, get a little more in shape than you've been in the past. You can do some like push-ups and stuff in your houses. If you can do like 100 push-ups, that's a pretty good number. 100 push-ups is a pretty good like tricep exercise, a pectoral exercise. But some people don't realize it's also an ab exercise. 100 push-ups will take you like a few minutes, like 2 or 3 minutes probably. You need to be able to hold a plank for 2 or 3 minutes, which a lot of people actually can't do. So that'd be a place to start. Try to plank for 2 or 3 minutes. If you guys want to do that, go ahead and do it right now. But that's not really what we're talking about. In real life, we understand what we mean when we say working out or doing work or doing some. I'm working right now. Don't come talk to me. I'm working. But take all that stuff and throw it right out. Completely, just like empty your minds of the word work. This is the physics definition of work. Imagine a mass floating through space. No air resistance, no friction, no forces. And it moves distance d through space. Now imagine there's a very, very small force. Imagine there's a small forward force, or a small backward force, or a small sideways force. What will each of these forces, F1, F2, and F3, how will they change the speed of the object? Notice I didn't say velocity. We're actually going to ignore velocity and direction for most of this unit, which is great. How will F1, F2, and F3 change the speed of the object? Assume it still goes distance d, but how will each force affect the speed? Well, that was kind of a review of what we just said. F1 will increase the speed, F2 will decrease the speed, F3 will not change the speed, just change the direction. So in physics, when we describe work, we look at the mass and see if the mass changed. We don't look at like, oh, the force used up a lot of fuel if it's like a rocket ship, or used up a lot of like energy, it burned a lot of calories if a person did work. We don't really care about that. Look at the object the work was done on. If something speeds up, the force that sped it up did work on it. It did positive work. If this mass goes from 100 meters per second to 110 meters per second, then the force that made it accelerate did positive work. A force that slows an object down actually does negative work. If you're thinking about real life, that doesn't make any sense. You can't do negative work. But in physics, you can. You wouldn't say like, oh man, I did physics problems for 3 hours, but then I played Valorant for 1 hour. So that's 3 hours of positive work and 1 hour of negative work. No, you don't say that. But in physics, you do. In physics, there is such thing as negative work. A force that speeds up the object does positive work. A force that slows down the object actually does negative work. You would think that you care about the time. You say, oh yeah, well, sorry, I'll come back to that. F1 does positive work, F2 does negative work, F3, it won't speed up or slow down this object until it changes direction. F3 does 0 work. Even though there is a force, there's 0 work. The object has to move in the same direction. So we could talk about the time. We could say, oh, the longer the force is applied, the more work is done. And that's kind of true because, yeah, if I apply a force over a long time, it'll speed up my object a lot. If I only apply it for like a second, it'll just change the speed a tiny amount. So that's kind of true. If you know the force, you can find how long the force is applied, and that'll tell you the change of velocity. But since we don't care about the direction of the motion, we need to look at how far it's. This is going to sound a little weird. We need the direction of the force and the displacement. But time doesn't have direction, so that's not useful for us. You'll see later, our answer will have no direction. But if we're talking about the time doesn't have direction. So if we don't know whether the force is pushing forward and speeding the object up, or pushing backward and slowing the object down, then we can't use the time. So it's going to sound really weird, but in work, we never think about time. We only care about the displacement of the object as it experiences a force. So no time. Work is based on the force and the displacement. But we need a specific thing. We need the work to give us a positive value when the force speeds up the object as it moves. And we need the work function to give us a negative value when the object slows down as it moves. This makes sense. A greater force will do more work. And if the same force is applied over a longer distance, it'll do work. Like let's say, I gotta slow down a little bit. So let's say I have like a frictionless block in front of me, and I push it with a certain force over 1 meter, it'll speed up a certain amount. But if I push it and it moves 10 meters, and I'm pushing it the whole time, it'll go up to an even higher speed. So the more force I apply, the more work is done. But also, the more displacement that the object has while I apply the force, also there's a greater work. So work is based on force and displacement. We need one more thing. We need to somehow get positive answers when the object speeds up, negative answers when the object slows down, and the work should be 0 when the force doesn't speed up the object, it only changes its direction. If you have any ideas, tell me right now. How can we make this answer give us positive, negative, and 0 answers, depending on whether the object speeds up or slows down? There's a very interesting method they use. They use a cosine theta. For the object of mass m, it is being displaced, displacement d, while experiencing a force, F. The work done on it is F d cosine theta. So let's see if it makes sense. Do we get a positive answer when the force speeds up the object? Well, how do you speed up an object? You push in the direction it's going. Theta is 0. Cosine 0 is 1. So yes, we do get a positive answer when f and d are in the same direction and the object speeds up. What if f and d are in opposite directions? Well, the object will slow down, so we should get a negative work. And theta would be 180. Cosine 180 is negative 1. Great, yeah, we got it. A negative answer results when f and d are opposite directions because the force is slowing down the object. And finally, what if it's 90 degrees? What if I apply a horizontal force during vertical motion? The object would not speed up or slow down, at least in that instant in time. That would be the centripetal force example from the unit we just talked about. It will not speed up, not slow down. In a physics point of view, that's not doing work. Even changing direction does change the object's motion, but it doesn't do physics work on the object. When theta is 90, work is 0. So it's a really tricky concept. I definitely want to talk about it more in class, and I definitely want to show you guys some of these explanations in the book or in the video. That might be a little easier. But this is true. This is the equation, because it comes from imagining a rock moving through space. If you apply a little forward force, it speeds up, you did positive work. If you apply a little backward force, it slows down, you did negative work. If you apply a sideways force, even though you're doing something, even though you're changing the motion, physicists don't call that work. And the cosine theta makes the equation fit that explanation of work. So that sounds pretty weird, but that's how it is. And the same is true even when you're on Earth's surface. So this is going to be like the very strange example, but here goes. If I walk into my classroom and I pick up like a desk, when I lift up the desk, am I doing work? And then, if I hold the desk over my head, am I doing work then? Do I do work lifting the desk? Do I do work holding the desk? Tell me what you think. So the space examples, we always said, oh, if it speeds up, you did work. If it slows down, you did negative work. This, we're actually going to ignore the speed. Assume it's moving very slow, or assume it's moving the same speed, or assume it starts at rest and ends at rest. However you want to think about it. We're ignoring speed. If I lift up a desk, I'm applying upward force, and there's an upward displacement. So there is an F, there is a D, there is a cosine theta, and theta is 0, cosine theta is 1, FD cosine. Positive work. Lifting up a desk is positive work. That makes sense, that's fine. But holding a desk, even if it's a super heavy desk, I'm holding it right over my head, I am applying a force, but there's no displacement, no work. Holding a desk up in the air, no matter how heavy it is 0 physics work. In the physics definition, you're not doing work. And this gets even weirder. What if I'm moving the desk? What if I have to pick up the desk and say, I want to over there? So I pick the whole desk, but I walk 10 meters away. I do have displacement, and I am applying a force, but the force is upward, the displacement is horizontal. FD cosine theta, even if I apply 10,000 newtons of upward force on this desk, and I walk 20 kilometers across horizontal ground, it's a very large F and a very large displacement, but theta is 90, cosine theta is 0. There's no work done. So we'll talk more about why work is so weird and why physicists like this definition later. But for now, work is done if a force is applied and the object is displaced in the same direction. If they're opposite directions, it's negative work. If it's 90 degrees perpendicular, it's 0 work. So work depends on two vectors. Strange note, work is a scalar. It has no direction. Not a strange, but an important note, work is measured in newtons times meters. Cosine theta has no units because it's a ratio. A Newton times a meter is a kilogram meter per second squared times a meter, but there's a nice simple name, a joule, capital J, joule. So, quick practice problem. If I do if I apply a 100 Newton force on a 4 kilogram rock that's flying through space at 15 meters per second, and it travels 8 meters. How much work did I do? You could solve this for the final speed already, if you wanted to. You could say, oh, A equals F net over M. 25 meters per second squared. We don't have time, but we can still find the final velocity. If we wanted to, we could do v squared equals v naught squared plus 2ad. So 15 squared plus 400, 625. So if you wanted to find the final velocity of this rock, you could. This is not new. We're actually not covering like a new idea. This is just like mathematical ways of manipulating stuff we've already talked about. But that's okay. If I push a 4 kilogram rock moving 15 meters per second for 8 meters with 100 Newton force, the speed will go up to 25 meters per second if I push it in the same direction. Now just a brand new calculation we can do the same numbers. The work done is FD, 800 joules. Why is that relevant? I'll try to come back to this next video. Pretty short video, so we can do one more calculation based on that. What would it be if the force I applied were the other direction? The work calculation is pretty simple. FD cosine theta, 100 newtons, times 8 meters, times cosine theta, cosine 180, negative 800 joules. But for practice, for review for you, find the final velocity in this situation. If the object is pushed backwards with this force while it moves forward. So you can do that right now. Okay, that is the definition of work. There's nothing else to say about work. It's a weird calculation, and you do some weird stuff with the direction of force and direction of displacement, but that's the rule, and hopefully it makes more sense later. Bye-bye.